So I'm going to jump over a little bit of the business stuff and some of the stuff at the beginning, particularly because she already covered it, and I think she did a pretty good job. So that's pretty cool. For those of you guys who haven't heard of us, we were founded in Japan. Explains the name a little bit. We've been around for about 4+ years. Really only commercially available for the last one. In terms of where we are, we're pretty much all over the world at this point. We have offices in Japan, obviously, offices in this city where I am, and then we do some development in Barcelona as well. This pretty much mirrors the slide you're going to see from a lot of guys in terms of partners, at least. Just like everybody else, we're installed or at least compatible and certified with all the major brands that you've heard of, all the distribution methods, and then for us as well, a lot of the hardware partners, which we can talk about a little bit later. This is kind of a slice of who we have in terms of our install base. This slide is a little bit old because it's changing always, but these tend to be the people that are running their public or private clouds on top of our current infrastructure. Okay, so I said I'd skip over this stuff, and I'm going to. But just as a basic idea, we provide what you would kind of expect in terms of SDN, right? We're a software-based SDN, just like PlumGrid. So we provide the basic functionality that you would expect from that kind of provider. Layer 2 through 4, NAT, both stateless and stateful, firewalling, load balancing, all that kind of fun stuff. Various tunneling technologies, take your pick. And then, of course, since that's a pretty limited subset, we also have a set of features on top of that that we leverage to provide more advanced functionality than, say, Neutron is capable of. One of our key differences, and by the way, I really like the questions. They were like the 3 major differentiations between us, so I'll get to those later, is that we don't really, even though our primary use case is OpenStack, we don't really measure what our support level is in terms of OpenStack. What I mean by that is that typically OpenStack is 1 to 2 layers above what we actually do. So since we're not dealing with it most of the time, our actual support matrix is measured on hypervisors instead. So that being said, right now we support KVM as our primary, Zen, ESX, some bare metal stuff, and some Docker stuff as well. You can also just run it straight on Linux if you feel like. And then any hardware underneath that, of course, that's x86 based, and on top of it, whatever distribution of OpenStack you'd like. Okay. So this is a little confusing when it appears early, but it should give you a better idea of kind of how things are oriented. It'll relate a lot to what was already said. You have sort of your underlay on this side. By the way, how many people here are relatively familiar with SDN and overlay networking, what they would say? How many of you guys have deployed some form of Neutron in production? It's a fairly large number. All right, so I'll kind of skip over some of this stuff. The point of overlay networking is that you can kind of separate out this software layer at the top, up here, from the hardware layer at the bottom and have them really not affect each other. So I can have sort of an arbitrary set of configurations and connections on the bottom, where this sort of gray diamond is. And I can programmatically determine through software what the topology and outlay of the top part is in virtual space. And I can change that on a programmatic level. Okay, so that's fine. But let's talk a little bit about how we actually do this, because this is really the best way to understand. And you'll kind of see where some of the differences come in. We basically have 2, but really 3 components on our basic install. I should back up a little bit and say that we have 2 requirements for where we deploy. One being that the hardware that you install on is x86, as I mentioned. We'll have ARM support at some point. And the other being that the fabric that you run this on top of be IP-based. So none of the proprietary stuff. That being said, those are our only requirements. So what the topology is, how it's racked, what sort of setup you use. We don't care as long as the endpoints are IP available. What these boxes are, who they come from, how recently they fell off the back of a truck. That is entirely up to you. Okay, so that being said, back to the components. We have up in the upper left, we have this little thing which is meant to designate our database component. We have a passive database cluster made up of very common pair of databases that you guys are probably familiar with, Zookeeper and Cassandra. We run them in a clustered mode, and we use Zookeeper to do storage of our topology information, basically the virtual and the physical topology. And we use Cassandra to do storage of everything else, so metrics, health status, that kind of thing. That's run in the standard configuration straight off the box, so if you guys have ever used Zookeeper or Cassandra before, you already know how to do that. The second component, which is this stuff on the green hypervisors down here, is our agent. It's written in mostly in Java with a little bit of Scala mixed in, and it runs in user space on top of the Linux kernel on any hypervisor that you're going to have. Pretty straightforward, just a standard install. The third component up here on the right is actually the same as the second component. As she mentioned before, most SDN vendors have a concept of a gateway. What that gateway is a little bit different. Ours is just a standard Linux white box running our agent on it as well. The agent will do the same processes as it does on the actual hypervisor, except with a little bit of extra muscle. We leverage BGP to do outbound connections to the rest of the upstream network. These boxes, as I'll show a little bit later, are all available. They're all distributed, and they're all failovers for each other. So you can buy as many white boxes as you want, plug them in. They'll all route properly the way that they're supposed to. If you lose one, they all automatically reroute. And you can do cool things like have a packet flow go out one and come back in another. Cool. All right. Apologies if I'm rushing a little bit. Feel free to interrupt me with questions. The point of doing all of this stuff, right, is to build a virtual overlay on top of our physical overlay. So once we have all of this stuff hooked up, we actually have to build a virtual overlay. In this case, it's going to be something really simple like this, but it's just for demonstration purposes. I should say that there are a number of ways that you sort of interact with our system to do this. You can either hit our API directly with one of our clients, like we have a CLI, we have a web UI, we have a REST API, all that stuff. You can, in most cases, for most functions, you'll probably be using the upstream OpenStack tools. So things like Horizon and the Neutron CLI, you'll just be interacting with those directly. And Neutron, through the provider plugin that you configure, or you just set the flag for it, we'll be dumping that directly into our API. So any number of tools you can use, you'll be interacting with our network. For the average tenant, they'll probably be just using the same OpenStack tools they're used to, since they're not going to be doing administrative functions. And you, as the administrator, will not really be straying outside of those same OpenStack tools 90% of the time. If you want to do some advanced features that aren't available through Neutron, then you can use our tools directly. But it's specifically designed so that you don't even really have to know what's going on in the background as a tenant to know that, or to have this stuff work, right? Okay, so let's assume that we're going to create a really simple setup here. We have a notion called a provider router. This is in virtual space, by the way. And this is kind of outside of what OpenStack understands. OpenStack doesn't have a concept of a provider router. But we use that sort of as a logical aggregation unit for traffic that's destined for stuff outside our network. So let's call that the internet in this case. And stuff that's coming in from the external network as well. So all of that is at least in virtual space, aggregated into this provider router concept for at least us humans to understand. And that is outside of the view of OpenStack, i.e. it does not live in OpenStack's database. Underneath that, from there on down, we just follow the OpenStack model. So we have tenant routers, we have tenant networks, we have VMs attached to those. They're owned by tenants, and if you allow the ability to do so, tenants can create these arbitrarily and mix them up and attach them in all kinds of ways that they want to. Pretty straightforward standard stuff, right? And of course, unlike some of the other options, you don't have to worry about IP address overlap or tenant isolation or anything like that. It's all straight down to the kernel level. It's isolated for every network interface that's created. Okay, so we're going to use this just for the following demo. I know it's really simple, but keep in mind you can make it as complex as you want. So as I mentioned before, the component that stores all of this information is our Zookeeper database in our database cluster. Again, you can access that in any one of those tools, and we'll store the initial configuration in there just so that we can pass some packets around and see what happens. So let's do the actual important bit, because this is where some of the key differences are. Just for the sake of argument, we're going to have the VMs be on different hypervisors, but it doesn't really matter. It's essentially the same process, whether they're on the same different boxes, different data centers, that kind of thing. Of course, the first thing that happens when a VM tries to pass a packet across is that the first packet will come up the channel, and it will hit the kernel on that box, or the hypervisor, depending on which hypervisor you're using. The kernel in this case will perform its standard networking stack on that packet, go through a bunch of different stuff. And if any of you guys are familiar with what that stack looks like, you'll know that one of those steps is called a flow table lookup. Essentially what it means is the kernel is checking its onboard flow table for any existing flows or tunnels that the packet can be passed across to get to the expected destination. In this case, since it's the first packet, there's no flows there, so we get what's called a flow miss, which you mentioned before. In this case, this is where the fun happens. Instead of using our own custom kernel module, we use a direct netlink channel to the kernel upstream. So you can use a regular kernel out of the box. And this packet information, when a flow table miss happens, is passed up that netlink channel to our agent running in user space. The next step, of course, is that our agent has to have a view of the topology of the network in order to do its functions, right? So it has to go grab the topology that we stored earlier. I will say, since you guys are a little more sophisticated than this was intended for, that this sort of action almost never happens. The reason that we use Zookeeper, for you guys that are familiar with it, is because it has what's called a publication subscription mechanism, which means that each one of these agents on the box is actually subscribed to a subset of the network data stored in Zookeeper, so that when a change happens to that data, say I go to the API and I change something, or as a tenant I destroy a network, Zookeeper automatically out of band will push that data to the relevant agents and will update that data cache on the local box. So the reason I say this never happens is because the agent really never has to go off box to grab state information at the time, because it already has a local cache that's been updated, importantly. I should say that all of these agents are stateless. So the reason I said almost never happens is because the one time it does happen is if you bring down an agent and bring it back up and then immediately need to restore the database, it will have to go off box and grab it. Was there a question in the back?
Yeah, it is a little off topic maybe, but I'll ask it anyway.
Sure.
So what you described is eerily similar to what CoreOS does with etcd and configuration files and so forth. And I was just wondering if you looked at that and had any comments on how the two might compare.
The reason I'm laughing is because, yes, that's my primary job these days. I don't know what I can say about this. So we have a stealth project that is coming out soon that will use that. I probably said too much when I said that, but yes, we're very aware of that, and we're very aware that this is an eerily similar mechanism to what CoreOS uses, and TBD is all I can say. Yeah. Sorry. But essentially, that's kind of what it's designed to do. Is it's designed to be distributed and stateless. Yeah.
So does that mean every host connected to that network, whether L2 or L3, if they're connected somehow to the different hosts through L2 or L3,
Yep.
that host will have all the basically routing information, LPN routing information?
In a sense, yes and no. It will have some slice of that network information. As you're probably getting at, having the entire routing information for each agent would be kind of burdensome.
Right.
So what, in fact, these guys have is that this one, this hypervisor, this agent down here, will have all the relevant routing information, we'll call it for a second, for the VMs that are connected to this box, and then any tunnel information for already established tunnels. So what I mean is it has a subset of the entire information that's stored in Zookeeper for the ones that are relevant to its local VMs.
What about like if the blue network talking to that green network there can reach each other? Is it going to have the information for that green network?
No. And the reason we don't is, you'll see in about 1 second, we don't actually store any of the routing or say NAT information on the agent side. What we do is we translate that into a set of what we call chain rules that are then applied to each agent. But let me put a hold on that question for just a second.
And the other real quick question
Sure.
that you just covered, are you modifying the IP stack or are you using the standard Linux kernel?
Yeah, so this is kind of one of the things that I don't mean to highlight our differences, but I kind of want to give you a sense that there's other options out here for everybody does it a little bit differently. We uniquely use a standard upstream kernel. The evolution of this is that for a while the kernel didn't have a good mechanism of communicating network information back and forth between it and other components. So what we chose to do originally was to use the kernel module that OVS used to do state information exchanges with the kernel. Some other people notably picked other kernel modules, but there was some issues around having an out-of-band kernel module loaded into the kernel itself. Luckily, one of our contributions to this was to push it into the upstream kernel in 3.2, and some subset of that code became the netlink code that's in there now. So we just use a plain vanilla upstream kernel.
You don't do any kind of data plane acceleration, like outside of the kernel space?
We do if you have offloading cards. So one of the slides that you saw earlier said we support multiple tunnel technologies, and the reason that we support technologies outside of GRE is so that you can do tunnel offloading on certain cards. But let me get to that afterwards. Okay, so we've got the state information. That's all well and good. Here's where the cool magic happens. We do something called simulation of the network on the agent that's on the local box itself. By simulation, I basically mean we walk the packet across the virtual network as if it were a physical network and do a transformation or any necessary transformations for that packet depending on what that step in the network would be. So in this case, we're doing a subnet address translation, a few other things, but basically just hopping it across the one part of the network that spans this in virtual space. The whole point of doing this is to create a set of tunnel headers. In most installations, it'll be GRE tunnel headers that we can then pass back down to the kernel and install directly in the flow table so that the kernel can establish a tunnel to the correct endpoint and pass that packet across. Just like that. That's basically the meat and potatoes of how this works. That's a pretty simple example because it doesn't transit much of the network, but if you were going off box, you would be doing the same thing except transiting the virtual part of the network that would go all the way to the external part. That's a little bit hard to visualize, I apologize, but basically what it ends up looking like for the agent side is, as I mentioned, we have what's called a set of chain rules. Chains are groups of rules. Each rule represents essentially a step in that process, and the transformation that's needed to make that packet go over that virtual step in the physical underlay. So that can be things like NAT translations, be security group evaluations, load balancing rules, all that stuff. They pretty much look exactly the same in our database. But what each one of these agents is designed to do is, in rapid succession, evaluate those rules for each packet, create the tunnel headers, about 14 bytes, and then push them back down to the kernel. So the very last little bit here is that now that we have this tunnel established, most transactions are going to be more than one packet, obviously, so we're going to be passing multiple packets. The good news is that subsequent packets that come up are going to be applied to the same process, so they will still be passed across the kernel networking stack. They will still hit that step that involves looking up in the flow table whether there's an existing flow, except that now we've already installed the flow, so it just goes straight across the existing tunnel and is dumped at the appropriate endpoint. In case that wasn't brutally obvious, it means that it doesn't have to go through any software outside of the kernel space. It's essentially just kernel line networking at that point, and you can achieve near line speeds for the subsequent packets as you normally could in old-fashioned networking.
How is that different than just putting a header on it to a physical layer 3?
It's not a lot different. It's the calculation is the key part. So it's the construction of the headers that are important. Once we have the headers, we just stick them in the flow table, and it's pretty simple from there on. And the reason we do that is on purpose, is we don't want things like, we don't want to have the OVS model where we have to, dick around with each packet and reconstruct that value when we already have this pre-built mechanism for doing the actual routing and tunneling. If we can create data that it understands, why not just use that completely? So a few more bits. I'm going to skip over this stuff because it's almost exactly the same. As I mentioned before, all of these agents are stateless, so they can be brought up and down at will. This is the standard Zookeeper cluster. Right now, we also have a pass or an API layer that's the same as the Neutron API. As she did a wonderful job of explaining before, Neutron is essentially, at its best, it's a plugin model. You can install Neutron, pick a plugin of your choice, enable it in the configs, and the plugin provider code will do the right thing. That's great. We love that. What it means is that the Neutron API essentially becomes a pass-through layer, right, for commands issued to the standard OpenStack endpoints. But that also means that Neutron is not aware of all of the capabilities of the API that you're pushing against. And it also means that you have at least two APIs, right? You have the Neutron API that's accepting the stuff northbound, and then southbound of that you have someone else's API, hopefully just one, that's consuming those from the Neutron side. So as part of our sort of due diligence, and now the fact that we've open sourced all of this stuff, what we're working to do currently with the Neutron community is get rid of our API, right? So all the concepts that we're capable of, all those extended features that our API provides that Neutron does not, we're pushing those all upstream. They're all going to be Neutron. They're all going to be part of the Neutron product. And our eventual goal is to get rid of our API completely and just hit Neutron directly and have our agents get their interactions directly from Neutron. So I assume I'm running out of time. So I will leave time for questions. Anybody? If there's no questions, I'll keep going. Just kidding.
You guys support hardware VTEP gateways?
Yes. So that was the stuff after this slide. It's roughly the same as what you would expect. Essentially, we can manage VTEPs on hardware boxes that support the OVS-DB protocol. Yeah, and then we can terminate the VXLAN stuff on that. And we have a number of people that are actually utilizing that directly at the moment. Any other questions? Cool. All right.